Good morning. So we're going to get started with amino acids. So we will see. Should finish this up relatively quickly. There's not a whole lot left. We had talked about primary structures and secondary, different types of secondary structures. So looking at these, I want you to look through A, B, C, and D, and I want you to tell me if they're indicating a type of primary structure, a beta pleated structure, an alpha helix, or a triple helix. I'll give you just a minute to do that. Okay, so looking at these different sentences and what they're describing. The first one, a polypeptide chain held side by H bonds. So hydrogen bonds are going to be some type of secondary structure. Remember, a primary structure is when you just string the amino acids like pearls together, and those are polypeptide or peptide bonds. So if it's got an H bond in it, that's going to be some sort of secondary structure. If it's side by side, that's where we get that folded side by side accordion. That's going to be our beta pleated sheet. The sequence of amino acids in a polypeptide chain. So how are the amino acids arranged? That's all a primary base thing. That's like the sort of first structure. You've got your amino acids, which are your letters, and then stringing them together in words, that would be your primary, and then we continue to increase complexity from there. A corkscrew shape with H bonds between amino acids, that is our alpha helix. All right, we get that twisted shape. And then 3 peptide chains woven together, that's just the triple helix. So a lot of definition stuff. So select the type of tertiary interaction. So tertiary interactions are when you already have like one of these secondary structures, whether it's an alpha helix, a triple helix, or a beta helix, and then it begins to fold in on itself because of things like disulfide bonds, ionic bonds. It could be an H bond, or it could be some sort of hydrophobic or hydrophilic. I would not expect you to know how these two things interact with each other, okay? How the amino acids interact with each other, because that would require you to have, know what leucine and valine is specifically. Leucine and valine, they both happen to be interact with each other in a hydrophobic way. Cysteine has sulfur bridges because it has a thiol attachment. Aspartic acid and lysine create an ionic bond, and serine and threonine have H bonds. This is kind of above your pay grade, so I wouldn't stress too much about that. All right, so some of the tertiary structures, right? We've got our primary, which is stringing the amino acids together. We have the secondary, which is like an alpha helix where it coils in on itself. And then we have a tertiary structure where the coil, right? Whether it's a helix or a triple helix or a baited pleat, whatever that is, will start to clump or fold in on itself. And when it folds in on itself, there's different ways it can fold in on itself. One of them is a globular protein. In a globular protein, it will fold in on itself. The protein will fold in on itself in this sort of ball-like structure. It's super compact. It has this sort of spherical shape. This thing does a lot. These sort of globular proteins are really good at carrying out like transportation, like hemoglobin. If you've heard the word hemoglobin in your blood, that's a globular protein. It's also good for metabolism and synthesis, great way to store oxygen, great way to transport things. Fibrous proteins consist of really, really long chains that form these very long shapes. Alpha keratins, which make up like hair, wool, skin, and nails. So all these things that have this really long sort of fibrous quality to them, they need to stretch, usually have also have a fibrous protein, right? So kind of what you're seeing on the macroscopic scale is what's happening on the microscopic scale. We have alpha keratin over here, which contains an alpha helix. We find this in hair and wool. We also have beta keratin, which is made out of beta pleated sheets. That makes a little bit of a different macroscopic thing. Feathers, which are a little bit broader and wider, are made out of beta keratins versus hair and wool, which is really thin and narrow and skinny. So do we have another type of structure? Yeah, we have a fourth one, the quaternary structure. All right, and the quaternary structure is a combination of two or more what we call protein units. So like one of those globular proteins, if we took a globular protein and like a couple other globular proteins and threw them in a box, that would be considered a quaternary structure. It has to be two or more protein units. It usually consists of 4 polypeptide chains as subunits in, for instance, hemoglobin. So here's hemoglobin, and it's got 4 different things. So going back to the phone cord, right, the twisting phone cord, that would be a secondary structure. Taking the phone cord and squishing it into a ball would be a tertiary structure, and then taking that ball and sticking it in a box with 4 other phone cords, because we don't use those anymore and we're gonna throw them away, that would be a quaternary structure. How these things grip to each other, like why they stay connected, is the same interactions that you would expect to see in a tertiary structure. So those salt bridges, those ionic interactions, things where like the R groups that are sticking off the amino acids stick onto other R groups or clump together. So here's an image of like the ordering of everything, right? So we've got a primary structure, which is just chaining the amino acids together with a peptide bond. Then we somehow create a secondary structure where the R groups sticking off the ends will make a more efficient structure. Then this thing will fold in on itself. So here we can see this is a helix and it's bending in on itself to make, in this case, it looks like a globular protein. And then we can take that globular protein or whatever that protein structure is, and we can stick it with other protein units to make a quaternary structure. So they build off or piggyback off of the previous guy. This is a good structure, or this is a good table to just sort of summarize all of the differences between primary, secondary, tertiary, and quaternary. So again, a lot of this is like definition based, right? I could ask you, is this an example of what sort of primary structure, or what sort of protein structure is this? And I could give you a triple helix and you would say, oh, that's a secondary structure. Or, oh, when R groups interact with salt bridges, where would that fall under? And you would say, oh, that's a tertiary or quaternary structure. So let's look at this. Okay, so go A through E. I want you to tell me if you would put this under the category of a primary, a secondary, a tertiary, or a quaternary structure. Okay, so identify each of the following at their protein structure level. So a beta pleated sheet is a classic example of a secondary structure. Ordering of amino acids within a protein, that is a primary structure. The first thing we do is order them and then connect them together. A protein structure with two or more peptide chains, that would be quaternary. So that's like taking two protein units and sticking them in a box together, a unit together. The shape of a globular protein, so a globular protein is a tertiary. Globular, fibrous, those are all going to be on the third level of structure or ordering. And then disulfide bonds between R groups, that's a tertiary. You could also say that's a quaternary. Quaternary structures can have that disulfide interaction as well. So proteins do this thing known as denaturization. And denaturization involves the disruption of the bonds in the secondary, the tertiary, or the quaternary protein structure. So denaturization isn't affecting the actual like main chain. It's affecting from secondary on. When a protein denatures, it sort of starts to fall apart or change. And there's a couple different ways that you can denature a protein or disrupt a protein. One is heat and organic compounds. So here's the denaturization of the protein within an egg. So when you have the active protein, it has a very specific tertiary and secondary structure. When you heat that egg up, it's denatured into this different sort of structure. This will disrupt, its tertiary structures. So how do we get from here to here? Well, what did we do to the egg? We cooked it, we heated it up. The thing with denaturing a protein is you can't go back, right? I can't take this cooked egg and make it uncooked again. So denaturization of a protein, breaking apart those second, tertiary, or quaternary, it changes it for life. So heat, adding an acid or a base, heavy metals and salt, and salts can do this, and then also agitation. So anytime you add like a really strong acid or a base that will break apart the hydrogen bonds specifically within polar R groups, and it can disrupt ionic bonds. So this is something acids and bases can throw off the tertiary and the quaternary. Heavy metals in ions that react with the sulfur-sulfur bonds can form solids. And then agitation, that's the last one. That's like these are all kind of chemical in nature. This is mechanical. So you're doing a physical act to denature the protein. An example of this is when you whip cream. So you can't take the cream and whip it and then like have it go back because you've denatured the protein. Specifically, you've stretched out the protein chains. So the protein chains used to be kind of clumped together and you've stretched them out. And that's what gives it that sort of airy quality to it. So as far as temperature is concerned, anytime you heat something above 50 degrees Celsius, that's kind of like the cooking temperature. Also, so you have to cook your food then, and also like autoclaving surgical items, or when they clean surgical items by heating it up, what are they doing? They're denaturing the protein within any bacteria that's on there so that they can reuse it. Acids and bases. So like lactic acid from bacteria will denature milk protein, and that's how you can change something from milk to yogurt and cheese. Organic compounds can have an effect. We use things like ethanol and isopropyl alcohol. You guys probably have isopropyl alcohol in your medicine cabinet, and you use that to disinfect wounds. What's happening there, the isopropyl alcohol or the ethanol, which is just alcohol, like vodka or something, is going to denature any bacteria that's sitting on the skin there. Heavy metals like silver, lead, and mercury can have a denaturing effect, and that can actually happen within people. So if you're consuming large quantities of heavy metals, not that you would do that on purpose, but if you were doing it, let's say through your water source, that can have an effect literally on the secondary, the tertiary, and the quaternary structures of your protein. And DNA is a type of protein. And then agitation, so whipped cream, meringue, those sorts of things, where you're taking an egg or you're taking a milk product and you're whipping it into something a little bit fluffier. So tannic acid is used to form a scab on a burn. So they take tannic acid, which is an acid, they put it on if you had a burn, and it will help to like quote unquote seal or heal because it's denatured the skin. An egg is hard boiled by placing it in boiling water. We've denatured that egg, we've cooked the egg. What is similar about both of these events, because like a scab, forming a scab and a cooked egg don't seem like there's a whole lot going on in common, but what is happening in both situations is you're denaturing the protein. It's so gross, right? Comparing a scab to a boiled egg. That's like very unappealing. Okay, so you do want to know these things about denaturing proteins. Let's see a question or two on them. Again, a lot of this is like really definition based. The last thing I want to talk about are enzymes. So what is an enzyme? Enzymes are proteins. So enzyme is a type of protein. You probably heard enzymes in your body. Oh, I'm taking a supplement with enzymes. What is it? Excuse me. Enzymes are protein that act as biological catalysts. Okay, so we've heard of catalysts before. A catalyst is something that speeds up a reaction without being consumed within the reaction. So you can reuse the catalyst over and over and over again. An enzyme is that. It is a catalyst. It just happens to be made out of proteins instead of a lot of times the catalysts we see in inorganic chemistry are things like just like a metal, like nickel or platinum. These are much more complicated. So how does an enzyme work? Well, we can get back to look at it here. So an enzyme, use our cute little enzyme in gray, will have a spot on it that we call its active site. And the active site has a very specific shape to it that what we call a substrate can come into. And a substrate is the thing that's going to be transformed or changed. This is sort of the substrate is the reactant, and then you get products. So what will happen is this substrate that we have in our body, and let's say our body doesn't like the actual substrate, it wants it to be broken apart into something else, like sucrose, and we want it to be fructose and glucose so we can actually digest it or use it. So the substrate will come in, it'll click into the active site. The enzyme will run its course and break the substrate or change the substrate, and you'll end up with a certain amount of product. Now, this process of the substrate clicking in, doing its job, and then becoming the product doesn't change this enzyme base. So the enzyme can then be reused again for another substrate, and you can use this enzyme over and over and over again. And we can see here, so enzymes are just a biological catalyst. Catalysts, they catalyze nearly all of the chemical reactions taking place in the cells of the body. So when we're running a chemical reaction in the lab setting with inorganic chemistry, a lot of times we don't use a catalyst because the things we're using are really reactive. So you put them in a container together and they're going to do their thing. In our body, it's a much subtler situation. So the chemical reactions that are happening in our body really can't happen unless we have a catalyst. And a lot of the control of how quickly something happens, like how quickly insulin is released or our respiration processes, all these things are not being controlled by the amount of reactant that we're having. It's actually being controlled by how much catalyst is available. So if we look here, this is, so we've got the enzyme carbonic anhydrase, and I'll tell you guys how those are named. It lowers the activation energy for this reaction. So we have CO2, it combines with water, and we get bicarbonate, and we get H+. Traditionally, that reaction would follow this path. It would require a good amount of energy to get to the product side. When we add a catalyst, specifically this carbonic anhydrase, it drops the activation energy. So the hump I have to quote unquote get over, energetically speaking, is much lower. So it's like half the amount of energy. So if it takes half the amount of energy or half the amount of collisions or half the amount of product available, or rather reactant available, we can still produce a good amount of the product. So these catalysts will always increase the rate of the reaction by lowering the activation energy, but they themselves are not consumed. So the name of an enzyme is derived by replacing the end of the name of the reaction or reacting compound with an ASE. So if we have sucrase or sucrase, SUCRASE, that is the catalyst for sucrose. Why would we want a catalyst for sucrose? Well, remember, sucrose is a disaccharide. Sucrose contains fructose and glucose. Our body can do things with fructose and glucose. It can't do anything with sucrose. If our body couldn't break sucrose up, the sugar up into those simpler carbohydrates, it would be useless. So we have a catalyst that breaks it up for us. It can also be named based off of describing what the compound is doing. So oxidase is a catalyst for an oxidation reaction. Can also be a common name for a digestive enzyme, such as pepsin or trypsin. So enzymes that are classified by the reaction they catalyze. There are 6 main classes of enzymes. So all the other things sort of fall into one of these. I don't expect you to have this memorized, but if it's like undergoing hydrolysis, so that would be, like let's say we had a really long carbohydrate, like amylose coming from starch. And we wanted to break that amylose up into glucose because our body and our brains can use glucose. We would have to go through hydrolysis. So we would use this hydrolase to break that apart. So yeah, I'm not super stressed about that, but I do want to talk about this. So how the enzyme works and all these things. You want to know these definitions. There's not that many of them. It's a pretty simple structure. I mean, okay, enzymes are much more complicated than this, but you'll have a little idea of what's going on. So we've got our enzyme. Somewhere on the surface of the enzyme is something called an active site, and that's actually the name of it. The active site is the place along the enzyme where your substrate, and the substrate is the starting thing, can bind or can be catalyzed so that you can then produce the products. So we've got the active site. It's a region within the enzyme that fits the shape of the reacting molecule called the substrate. That active site is somewhat fixed. So a catalyst, there isn't like a universal catalyst that'll catalyze everything in your body. It will only catalyze like a specific thing because of the shape of the active site. It contains amino acid R groups that stick off, and then it will bind to the substrate. So we can see that here. I've got all these amino acids that are right at the rim of this, and it's got R groups sticking off. So this has like a CH2OH group, and that can make hydrogen bonds with a amino acid that's on the substrate. So that's how it sticks together. When it releases the product, or it will release the product whenever the reaction is complete, whatever it is. And again, this is a very simplified definition of this, but in an enzyme catalyst reaction, this is what the enzyme catalyst reaction looks like. So we have the enzyme, which is represented with an E. We have the substrate, which is symbolized by an S. And these two things are separate. They first step will come together and they form the ES, or the enzyme substrate complex. So this is where the two are sort of fused together through their R groups. At this point, you could go back to being an E and an S, right? The enzyme and the substrate. And that happens on occasion. The enzyme and the substrate come together, and for whatever reason, they didn't click in properly, or it's just the enzyme is no longer effective. It can break back apart into the original enzyme and substrate. But the job of the enzyme is to actually move forward in this. And what will happen is we will end up with the product, and we'll also end up with the enzyme. And what you see is the enzyme, which is in blue here, stays the same. Blue E, blue E, blue E. The thing that changes is the substrate. We have the substrate on its own. We have the substrate connected to the enzyme. And then at the end, we have the product. There is no double arrow between the enzyme substrate complex and the enzyme and the product. We can't go backwards. The job of the enzyme is not to take, like, let's say we were doing sucrose and we broke it into fructose and glucose. That same enzyme can't take fructose and glucose and smush it back together to get the sucrose. Because at the end, you're left with an enzyme that is the identical to the enzyme in the beginning, you get to use it over and over and over again until, you know, it gets old. So I feel like we've already talked about this one, but in the hydrolysis of the disaccharide sucrose, we've got our enzyme substrate complex is when the sucrose binds to the active site of the sucrase. That glycosidic bond of the sucrose is in a position for hydrolysis. So remember, when we have a disaccharide or any polysaccharide, they're connected with that glycosidic bond. That glycosidic bond is what ends up interacting with the enzyme group, and it breaks it. So the R group of the amino acid at the active site catalyzes the hydrolysis of the sucrose, and it will break it into glucose and fructose. The products of the structure are no longer attracted to the active site because it's been changed, so they get released. And we'll be left with our product in this case, which is fructose and glucose, and then the sucrase is unchanged, and we can thread it back in to start the process all over again. So there's a couple different ways that we can explain this enzyme process. One of them is called the lock and key model. And so in the lock and key model, the active site, that place along the surface of your catalyst, is very rigid and non-flexible in shape. So it's like there's no room for customizing. If you're a sucrase, you are only going to let the perfect sucrose at the right angle fit into you. So enzyme binds only to substrates that exactly fit that active site, like a lock and a key. The substrate is the key that fits the lock of the enzyme. This model, a note down here, this model was a static one that didn't include the flexibility of the tertiary shape of an enzyme and the way that the active site can also adjust. So this was a very simplified version. This is not really what's happening. This actually wouldn't be a very effective catalyst. It's too rigid, right? Its shape is that enzyme site. It's like you gotta nail it, or you're not going to be able to run the reaction. More effective way of running a catalyst and then thinking about it is this thing called the induced fit model. So there's two models that you guys need to know, the lock and key and the induced fit. In the induced fit model, the enzyme structure, specifically where the active site, isn't rigid, but it's able to adjust to the shape of the substrate. So the tertiary structures, or the third level structures of the proteins within the catalyst, can kind of stretch and expand a little or contract a little to fit a substrate that maybe isn't the perfect substrate. And in the world and in reality and in organics, nothing is really perfectly shaped. So it's much more efficient to have an induced fit active site. This gives a larger range for what specifically can fit in there. The shape will change to improve the catalysts during the reaction. So that catalyst or enzyme substrate fit is much better. We'll just run more reaction that way. So here's a picture of the induced fit model. So we have, let's start here. We've got an active site, and the active site is sort of making this like bottom of the boat shape. And here's our substrate, which is a circle. If we were dealing with the lock and key model, these two things would be too far apart to make magic happen. But what can happen is this active site can adjust, and it sort of meets in the middle and says, hey, it's not gonna totally change its shape, but it'll adjust enough, in this case, making a little bit of a box, and the substrate as well will kind of box out one end so that they can come together. And then you have your enzyme substrate complex, and then you release the substrate and you get your product, and the enzyme will actually adjust back to its original shape. So it kind of has a default active site that it will always return to, because, you know, this substrate here, this may be the one-off wonky sucrose that has a little bit of a weird shape, but all the rest are pretty aligned. Yeah, this is just much more effective. Now this, I do want to note that this induced fit model for this active site, this site doesn't change so much that it'll start to catalyze other things, okay? So don't get the idea that if this is sucrase for digesting sucrose, that all of a sudden you're gonna be able to like shove like, I don't know, some other thing, right? Or this isn't gonna start to work on like oxidizing things. It is specifically designed for that substrate. It's just a little more flexible. So we also have these things called isoenzymes. Isoenzymes are different forms of an enzyme that catalyze the same reaction in different cells or tissues of the body. So just like you see that word iso in other areas we used it mostly in our organic chemistry. but it consists of a quaternary structure with slight variations in the amino acids and the polypeptide subunits. So there are 5 isoenzymes of lactate dehydrogenases. This converts lactate into pyruvate. So there are actually 5 of these, depending on where in the body you need that process to occur. It'll have a specific one. So each of the LDHs, this lactic dehydrogenase enzyme contains a mix of polypeptide subunits, M and H. Different combinations of M and H are used to convert lactate into the product in different organs. In the liver, muscle, lactate is converted. Oh, what? Hold on one second. Sorry. My husband can never find his keys ever. And I tell him, I'm like, just have a spot, your key spot, right? Just have one spot for your keys. And he will not do it. He just will not do it. So it's a constant battle. My keys are always in the same spot unless he uses my keys, and then they're not. And then I get really angry. I gotta lay some stuff down. Anyway, okay. So this is getting a little out there, but we have these isoenzymes where you get a mixture of different ones, and that just helps to increase the effectiveness of the catalyst or the enzyme. All right, we don't really need to worry about that. Okay, so how can we affect enzyme activity? Or not we, like we're not consciously affecting these enzymes activities, but our bodies like to adjust to affect enzyme activity. So the activity of an enzyme, like how effective an enzyme is at lowering the activation energy of an equation, is called its activity. It describes how fast an enzyme catalyzes the reactant into its product. It is strongly affected by these sorts of conditions: temperature, pH, and then the presence of these things called inhibitors. So a lot of the catalysts in our body are in that catalyst enzyme, same thing, are really, really effective. And so our body, in order to control that effectiveness, they will create an inhibitor. So we also have these things called inhibitors, which don't slow the reaction down directly. The inhibitor will slow down the catalyst, will then slow down the reaction. So as far as temperature is concerned, optimal temperature is just shy of 40 degrees Celsius in humans. That's why our body temperature tends to sit around there. If we get into a colder environment, it will lose activity, okay? Sort of shuts down. If we go higher than 50 degrees Celsius, remember that was that denaturization cooking temperature. We have sort of cooked ourselves or cooked the enzymes. So body doesn't want to get hotter than that. Body likes to stay in this sort of narrow range of optimal temperature for enzymes. There's also a pH that the enzymes, and this again, this is in relationship to human enzymes, okay? There are other animals out there that have a different set of parameters for their enzyme activity. But for humans, usually there's an optimal pH of just under 7, okay, which is a neutral pH. If we add too much acid or too much base, it can have an effect on the R groups of the amino acids. So those little things that are sticking out from the amino acids, and it can disrupt the tertiary structures. Now, the body has an optimal pH of 7.4, but there are certain pockets within our body where there are specific enzymes that like a specific pH. Okay, so overall our body has a happy 7 pH. But if you go into like the belly of your stomach, what does your stomach have in it? It has acid in it. So any enzymes that are in the stomach are going to need to like be able to stand up to a really, really low pH. So pepsin is a very specific enzyme that has an optimal pH of about 1.5 to 2. Then we have, areas in the body, like if we go to the liver is a very basic area of the body. So the liver enzymes need to be comfortable with that higher pH. Again, overall, the body has a sort of a feel of 7. So sucrase, which digests or catalyzes sucrose, has an optimal temperature of 37 degrees Celsius and an optimum pH of about 6.2. Determine the impact of each change on the enzyme activity. So if we change the pH to 4, are we going to increase, decrease, or not change its activity? Well, if we're at a pH of 4 and it wants to be a pH 6, we are definitely messing with the enzyme. So we're going to decrease its effectiveness. If we're running the reaction at 70 degrees Celsius, we're not even just going to decrease the enzyme activity. We're going to like denature the enzyme. We're going to just break the enzyme apart at that point because that's very, very warm. So inhibitors, an enzyme inhibitor. And again, this is very simple, but they are molecules that cause the loss of catalyst activity, or they'll slow down the catalyst activity. And there's a couple different types of inhibitors. One, it prevents the substrate. Well, this is, I guess, its end goal. So how the inhibitor works is it prevents the substrate from fitting into the active site. So in order for the catalyst to work, the substrate has to fit in its active site. If for whatever reason the active site isn't available, the substrate will just bounce into the enzyme and then, float back out into the ether. So traditionally, we have something like this, where we have the enzyme and the substrate. They come together to form the enzyme substrate complex, and then we get the enzyme in the product. Well, what if there's an enzyme and it comes together with an inhibitor? Then we get this enzyme inhibitor complex that is preventing a product from being produced. And there's a couple of different ways it can do that. One is called a competitive inhibitor. So a competitive inhibitor has a very similar structure to the substrate. So like we could say that there's a competitive inhibitor for sucrase, and it looks very similar to sucrose. And so what it will do, and these slides of like, what is going on here? I guess it's going in either way there. Okay. So we have an enzyme, and traditionally the enzyme adds to the substrate, right? Those two things come together and we get our enzyme substrate complex, and then we get our enzyme in our product. Well, if this inhibitor is also available, the enzyme can connect with the inhibitor and form an enzyme inhibitor complex. Well, if the enzymes are being occupied with the inhibitor, they can't connect to the substrate. So the enzyme is a competitive inhibitor. This enzyme is a competitive inhibitor. This is a competitive inhibitor because it is competing with active sites from the substrate. It's kind of like, if there's 10 people and you need all 10 people to work for you, but somebody else comes along and is like, well, I'm a better fit, and they take 5 of those people, you're only left with 5 people. There's only so much enzyme available. Your body won't necessarily make more enzyme. This has an effect to, this effect though, it can be reversed if we increase the substrate concentration. So if we just flush the system with substrate, that percentage of inhibitor will lower, and we will see, a normalization of the catalyst, because it will there's just a higher percentage of substrate to interact with. is what it, what it looks like. Okay, we've got an inhibitor or an enzyme, and it's going to connect with the substrate, and we're going to get our product. Well, if we have an enzyme over here, and it's, instead of going to the substrate, it's going to the inhibitor, now the substrate has lost that opportunity. And if that happens, repeatedly over and over again, it can have an effect on how much product you get. So that's one way it slows down. We have another thing called a non-competitive inhibitor. It has a structure that is much different than that of the substrate. So it doesn't look anything like the substrate. It doesn't even bind to the catalyst at its active site. It will actually sort of plug itself into another site on the enzyme. And when it shoves itself onto the enzyme, it changes the shape of the enzyme. Specifically, it will change the active site of the enzyme. And when it changes the active site of the enzyme is no longer able to fit with the substrate. So it looks something like this. So we've got our enzyme, and it fits with the substrate, and we can get our enzyme substrate complex. Hopefully that makes sense now. Well, what will happen is we have the enzyme, and a non-competitive inhibitor will shove itself in on the side somewhere, and it totally changes the shape. So whereas the substrate could sort of fit in this, there's no way it's fitting in here. And now it pretty much renders this enzyme useless. The thing with the non-competitive inhibitors, it doesn't matter how much substrate I add, none of them are going to fit in that active site. So with the competitive inhibitor, if you just add more of the substrate, if you add more sugar, you will be able to catalyze it with sucrase. That isn't the case if you use a non-competitive inhibitor. A non-competitive inhibitor changes the foundational activation site, so it will not interact with the substrate. We also have things called irreversible inhibitors. So in an irreversible inhibitor, it's a molecule that causes the enzyme to lose all of its activity. These are things that tend to be toxic. It pretty much destroys the enzyme. How that happens, this material will form a covalent bond with an amino acid on one of the side chains of the catalyst and totally render it inert. Nerve gas is an example of an irreversible inhibitor. Insecticides and antibiotics as well. So penicillin, how does penicillin work? It is a big material that will actually insert itself into an enzyme on the bacteria, have a covalent bond, and render that bacteria or the enzymes in that bacteria totally inefficient. Now, what can happen is bacteria is, ever evolving. It can change its enzymes, evolve its enzymes in such a way that penicillin is no longer effective at doing that. So how we've got our competitive, our non-competitive, and our irreversible, and how they affect enzymes. So you do want to have that. You want to know that. So identify each as an inhibitor that is competitive or non-competitive. I'll give you just a minute for that. Okay, so increasing substrate reverses this type of inhibition. That would be competitive, right? If it's a competitive situation, if one of them just becomes more concentrated, it'll balance it out. It binds to the enzyme surface, but not at its active site. That's the non-competitive. So the non-competitive still leaves the activation site open. It just changes its shape. Its structure is similar to that of the substrate. That's a competitive situation. Inhibition is not reversed by adding more substrate. That's the non-competitive. Right? So this is what I'm talking about when I'm saying it's like definition based. Oh my gosh, that's it. We're done. That's everything. You have learned everything that you need to know in Chem 130. So you do have one more test. You've got your 5th test, which is covering chapter carbohydrate and amino acids. And it's relatively definition based. I think you guys should do fine on it. That is going to be open to you all on Sunday and Monday, okay, at the normal times. Your final exam will be open Monday and Tuesday. Just want to double check and make sure. So Monday 5:10, it'll open at 5 a.m. To Tuesday 5:11, but it closes at 5 p.m. All right, your final will close early because I have to get your grades in at like 8 a.m. the next day. So I need to make sure that that is completed. There is some overlap on the time-wise for test 5 and the final exam. They're both going to be offered on Monday as well. So if you want to just like have a chem test day on Monday, you can do that as well. There is one more lab to finish up. It's this amino acids dry lab. A lot of it is just definition based. So yeah, I've got a couple labs I need to grade for y'all. I'm going to try and get to that. It will definitely happen by Sunday. These will be graded. If not Sunday, no, they will be graded by Sunday. They will be graded by Sunday. So if you have any other questions, feel free to stay around. If it's general, shout it out. If it's personal, just hold on and I will talk with you then. You guys have been awesome. Thank you so much, especially my consistent camera people who've braved the way and allowed me to see somebody. It really does help your instructors when they can see your faces. So, but hopefully we won't have to worry about this moving into fall. I think we're going to be heading back into person, face to face. So if you want to come stop by and see me in my office, I would love to meet some of you in person as well if I haven't. So have a really good weekend. Bye guys. Let me know if you need anything.